Thank you for inviting me to come and speak. I'm Violet Pfeiffer. I am a radio science software engineer at the MIT Haystack Observatory. The observatory is found on 99 Millstone Road in Westford, Massachusetts. I want to say that it's near other things, but it's really not. It's in the middle of the woods, very purposefully to reduce noise in terms of the data that's collected using the telescopes. So to reduce interference. I will primarily be discussing my work on the Haystack Observatory Post-Processing System, also known as HOPS. And a little more, I'm no longer primarily working on HOPS, but I've worked at MIT Haystack for about 5 years, so there is plenty to discuss. And do we do questions during the presentation or after?
Totally, you're up to you, what you prefer.
Okay. So I don't mind if folks interrupt me in order to ask questions. That's perfectly fine. Just please someone let me know that there is a question, since I'm not able to see that since I have this presentation as full screen. So the MIT Haystack Observatory is part of MIT, and it's sort of this satellite part of MIT that is in Westford. And most of the work I've done has been as part of the Event Horizon Telescope team, which is an international group of academics and engineers from various institutions all over the world that work together in order to generate science. So before I discuss the HOPS software, it's important to go over what is VLBI, which stands for Very Long Baseline Interferometry. The long story short here is, in order for us to do observations, so that, and by that I mean astronomical observations of, say, black holes, which are very far away, we need telescopes all around the world working in tandem, observing the same body at the same time in order to collect enough data to do the science we do. And the reason for that is, in order to observe these bodies correctly without many telescopes around the world, we would essentially have to have a telescope the size of planet Earth to observe them, which is obviously not reasonable. So they work together in a network. On the left here is an image of the observatory in Chile called ALMA, that is the largest and probably most well-funded observatory. They are primarily funded by the Chilean government. They are also funded by the National Science Foundation. You can see here there are many telescopes working here in tandem. And on the right here, I have a graphic from Wikipedia that illustrates how this very long baseline interferometry works. You'll see that there's an example telescope here in Australia, one here in ALMA, which is in Chile, one in California, and one here in Spain. So together, they are all recording data at the same time, pointed at the same object, and that is the data that we use. That is our input. Here's another graphic that is in more detail about how this works. It's effectively the same idea. You have a telescope here on one side of the world, another telescope here on another side of the world, and they are listening. That's one thing that folks get confused about often is I apologize for the construction downstairs. They often believe that we're like SETI or some other organization that's emitting data. We are not emitting data, we are receiving data, we are listening. And what that means is, typically, for example, if we're attempting to image a black hole, what we'll do is point the telescopes at the black hole and then point them to some sort of calibration source, which here there's a quasar. So you point it at the calibration source and then back the black hole, back and forth. And that is the basic way that we collect the data. And here's an example of how we get the data via high-speed data link. It is then sent to a correlator. I'm not a fan of the name correlator because it's very confusing, but it's effectively a supercomputer cluster with many servers. The one at Haystack has about 70 servers that work together to take what is effectively petabytes and petabytes of data and correlate it and make it basically usable for the scientists. And this is the end result after the data has been correlated. Then the Haystack Observatory Postprocessing software, it's really a software suite, is used to generate plots like this that scientists are able to use to determine the quality of the data that was received and make other such observations, for example, like imaging a black hole. So this is a plot here where on the top left it shows you which correlator it was the data was processed at. This is on the right here, we have which telescopes were involved. We have the signal to the noise ratio, which is an indication of the quality of the data we've received. And most of what we're calculating is the amplitude and the phase, just basically doing a lot of math in order to allow this data to be readable. So this is a pretty good plot here, and indicates, see how this red line, the amplitude, and this blue line are almost aligned. That means we have a very strong signal there and that we have done what we need to do. So you may be thinking, why what is the purpose of all of these graphs other than, here, look, my graph, isn't it amazing? The end result is actually this. So on the left here is M87, which is the first black hole that was imaged as part of the Event Horizon Telescope team. That was done in 2019, or at least the information was made publicly available in 2019. And on the right is Sagittarius A star, the famous black hole that looks like the canonical logo, which was released in 2022 to the general public. This project I was involved in, and the work I did, I was one of 300 people involved in the Event Horizon Telescope team that generated this image. So basically, from the plots I showed you and the other output data, HOPS outputs the data in different formats that the scientists use to then create these images. So the way they create these images is basically they take an average of all of the data over time, and that's how they are able to create an image. I guess like an example of that is, so if you imagine like there's a field and there's a tree on it and there's clouds going back and forth, and you want to get an image of the tree, you will take a lot of images and then use machine learning to basically generate the image of the tree. So it's sort of like what's most common in all of these sets of images. If that's a bit confusing, that's okay. You don't need to understand that part. But anyway, so this is the Haystack Observatory post-processing software is more of a software suite. It has many, many tools that astronomers use. It initially began in the 1970s and was initially written by Alan Rogers and Fortran. It has seen many versions and iterations over the years. the version I was working on was version 4. It involved several programming languages: C, C++, Python, Nix, Perl, Fortran, and shell code. We settled on using CMake as our build tool. The development environment we used was Ubuntu 22.04, and we used HOPS 3 as a test oracle in order to compare the results we were generating with HOPS 4 with HOPS 3. So there was a lot of refactoring that was done in the code in order to modernize it in HOPS 4. So we wanted to make sure that it was correct by comparing it with HOPS 3. Obviously, we used unit tests to make sure that the data we put in was exactly what we expected to get out, and compared them. And we also did regression testing. Do we have any questions so far? All right, so
yeah, actually, I had one. I'm sorry, I was slow to
Sure.
unmute there. So HOPS 3 and HOPS 4 are just totally separate, like running production environments that you were working with.
Sort of. HOPS 3 they're like different versions of HOPS.
Okay, so it's a different version of the software suite that you're running.
Yes.
So you were just using test 3, HOPS 3 as like this is the source of truth, comparing
Yes.
to the new environment, making sure the results are the same, et cetera, et cetera. Okay.
Exactly, because, as we were, there was a lot of data that, so astronomers like to make custom data types, and in their defense, a lot of these data types that they created were back before we had JSON and XML and these standard data types. So they came up with their own custom solutions. So it's like comparing apples and oranges, essentially. So that's one of the tasks that I worked on, was converting the data from these non-standard legacy formats that inherited what I will call Fortranisms, and ensuring that they're converted to JSON correctly and that they are exactly the same. So we encountered many challenges. We had a lot of legacy code and Fortran code. I was not familiar with Fortran. I still would not say I am particularly familiar with Fortran, but one thing I did learn about Fortran is that they do not have null terminated strings, which caused for some very interesting issues in my C++ code when converting the legacy formats to JSON. There were times when the JSON that was produced had just garbage in it, and I know enough from C and C++ programming that it looked like it was encountering unallocated memory or something like that. And I learned the hard way that Fortran does not null terminate its strings. We had custom data types that were from the 70s. So, for example, there were fields in there that were literally called unused 1 and unused 2, and comments that said things like, "I have no idea what this is for," which I had no idea what they were for either. It wasn't obvious to us, and not all of the folks that had worked on the software initially in the 70s, are still around or still available to ask questions. Not all the dependencies are documented. That is another challenge I encounter a lot while working on astronomy and geodesy software at Haystack. Essentially, no one ever did audits of what all the dependencies were. So, there were situations where everything worked on this one server, and then that server would go offline, and folks would try to install and update the software on a different server or on their own development machine, and it wouldn't work, and it wouldn't be documented that certain dependencies were missing. So there were some assumptions there. That was one struggle. Another was that a lot of software that was written by the astronomers assumes you were using X11 forwarding. So if you are working on a server, keep in mind a lot of this software, you can't process the data on your one machine. You need access to the correlator, which is the supercomputer cluster, and it assumes that you have X11 forwarding enabled. I'm not even necessarily sure why, because usually there aren't graphical prompts or any sort of graphs that you need to look at or observe. But I guess the assumption there is that you're sitting there and babysitting the data that's being processed. And there were times where I literally just had to press the space bar to allow the software to continue. Also, there was definitely some resistance to change. I did my best to say to encourage folks to allow me to containerize the software in order to make declarative environments that were reproducible for the code. And by containerization, I don't necessarily mean using Docker, because Docker is higher level than that. It includes an operating system. What I mean is the lower level Linux containerization using Nix, which is how I was able to do that. So I did do that a few times with individual code bases I was given. I would containerize it with Nix. I'd make a reproducible declarative build process. And in the process of doing that with Nix, I was able to audit all of the dependencies and document them and discover that there were many dependencies that even some of my senior colleagues weren't aware, because there was the assumption that you would use a specific version of Ubuntu and it would just come with some of that software installed. We did have a dispute between supporting with using make and CMake in order to build our code base. For a while, we were supporting both. It was a headache, but eventually we settled on CMake, which was good. Our input data, again, is anywhere between 70 to 100 gigabytes, which has its own challenges. Moving the data can, even from one server to another, could take a while. There have been times when I've attempted to download data and it took an entire day or two. It really depends on the hardware you have. Anything like an old network switch or a frayed cable that's no longer up to spec can be a bottleneck. And also working with binary data, I found that to be challenging because it's not like JSON that you can open up the data in your editor and inspect it yourself to see what is going on when you're troubleshooting, which was, really helpful for me when I was learning. But with binary data, that's not really an option. Typically, you depend on, hopefully, other astronomers have made some sort of API to open the data, which, mind you, might be in a custom data format in order for you to inspect it. And the data is typically stored in binary because that is the most efficient way to store data when they are doing experiments. Remember how I said there's petabytes and petabytes of data. This data is being recorded like that. Usually they record data over the course of 72 hours. So it's a lot of data. So it would take even more space if it was stored in a larger data format. So that's why at least the input data is typically binary. And last but not least, I am personally not a scientist. I do not have this kind of astrophysics or geodesy background. I am a software engineer. That is where my education is. I am a computer scientist. So for me, there was a lot of catching up to do in terms of teaching myself to be a subject matter expert and learn all this background information. So I felt like I was playing catch up with folks who have PhDs in astronomy. So that was certainly very challenging. This is the output for another project that I worked on for the NASA Goddard Geophysical and Astronomical Observatory. There, I was handed legacy code in a dead programming language from the 90s called SuperMongo. It has nothing to do with MongoDB. It is that is a misnomer, and I was able to update it and containerize it and document it and add a lot of quality of life features to it to generate plots like this. Essentially, this plot is used to determine if the hardware of this telescope was performant or not. That is something that is very important to check in terms of this data was used essentially to measure the rotation of the Earth, how fast the Earth is turning, which is used for determining time, and it is used for GPS data as well, that it allows GPS technology to work. So NASA does these experiments where they are measuring the speed at which the Earth rotates and then making that data public for a lot of our modern technology to be allowed to function. So you may be wondering, how do we get our funding? We get primarily our funding from NASA and the National Science Foundation. That is where my research lab is. It's 100% government funded. In that way, there are no private sponsors. We do not have access to the funds from MIT main campus. Something that folks often don't realize is that MIT is actually technically a nonprofit. And you may think, well, it's a private school. That seems ludicrous. And I don't know the details of how exactly that works, but essentially the research labs are primarily government funded. So they do not benefit from any sort of income that main campus has from providing students with their degree programs. And unfortunately, I feel need to address the elephant in the room. As of recently, there have been many cuts to government funding. This graphic is from Dr. Joshua Wheats and the team at UMD. It shows that the NIH has had $18 billion cut. NASA has had $6.8 billion cut. And the National Science Foundation has had $5 billion cut this year. So that is the unfortunate circumstance we find ourselves in. MIT is what appears to be in the middle of several rounds of layoffs. So there is a somberness in this work environment currently. And I personally feel that science is under attack, unfortunately. So I have here further reading. If you are interested, I have cited several papers. This one is a very good introductory paper if you're interested in learning about how very long baseline interferometry works. I have cited my paper that I've written with the HOPS team on the progress of our refactoring this legacy software. I've also included a paper in which I'm a first author here, which discusses how the phase calibration delay is done for the NASA GGAO telescope. So that was I showed that a couple of slides ago. And I've also included more information on imaging black holes for whoever is interested in that. And here's my contact info. thank you for listening, and I will take questions now.
I just posted in the chat, but my first question is where is the slide deck link? Because some of these links would be great to have.
Oh, I can send this. I wasn't sure who to send it to, but I am happy to send that to whoever will receive it.
If you send either the link or the deck to Jabber, he posts it with the minutes.
So Violet, this isn't a computer question, but they had to mess with the color palette on it M87, right? Did they to try to make it a little bit more orange? I mean, is there any visible spectrum coming off of a black hole?
No, it's all in the radio spectrum, so there's no visible light. So they did add those colors in order to make it readable, basically, for us humans that perceive everything in terms of light.
I was very upset when I found out at way too old of an age to find this out, that they colored the pictures taken by telescopes and stuff like that. It really bothered me that it was like, oh, wait, I thought that's how they took the picture. No, a lot of that stuff is colored in so that we understand it as people, because the data that comes back is not.
Yeah, I remember an unfortunate situation I had back in the 80s. The Voyager spacecraft had gone past Saturn, and I forget what magazine it was, but there was a spread in one of the magazines about all the things they discovered there. And I saw a photo of Saturn with a little hexagon at the top, and I just immediately assumed that this was a computer-generated image. And I was convinced at that point that the magazine was lying about these being photos. And it wasn't until like almost 20 years later that I found that it was an actual structure in the Saturn.
So here's a question I guess you might be able to speak to. Did the people at Haystack and you guys as developers coordinate with any other projects out there with regards to the format of the data frames that come in from this? So you said you dealt with a lot of binary data and stuff, and I worked at Chandra. We had the exact same issue, and there was a guy that created a product that made it all out into JSON, and we could see the telemetry and whatnot. Did you guys coordinate with others on that project, or was this because everything came from in-house, you kind of had to do things in-house thing?
Yes, we did coordinate with others. Our primary coordinators were at the Harvard Center for Astrophysics, specifically that they gave us a lot of the requirements that they required for the new version of HOPS in order to expand the type of data formats that it is compatible with and add new features. So this software is used by astronomers all over the world. They use it for their science, and it is also very tightly coupled with another astronomy software produced by an observatory in Australia. I'm forgetting the name right now of which institution that is, but it's called DIFX, DIFX. It is very tightly coupled, so much so that it's actually they ship their software out with HOPS, and so the reason that the software suite is so complicated is because we have different customers effectively that we have to satisfy. And by that I mean astronomers and geodesists that are doing different types of science. So, for example, geodesy, so that's the study of the Earth, its shape, and its rotation in space. They have much higher specs on their telescopes. We're talking about they need to measure changes in the telescope's direction on the picosecond level. So they require more data be stored and processed and calibrated as compared to the Event Horizon Telescope team, which their telescopes aren't as up to spec as the the geodetic telescopes. Did that answer your question?
Yeah, I think so. That was really helpful. Are you familiar with the Chow software? CHAIO, I think it is. Chandra uses it. I
No.
know that much. They use that in a system called Maud, but that's really for the operations and telemetry side, not the actual science data side. So maybe that isn't as familiar.
No, I'm not familiar with that, unfortunately.
Different type of telescope.
Yeah.
I have a
These
question.
are radio telescopes.
Violet, so in doing this rewrite or rebuild and transitioning from the HOPS 3 to HOPS 4, you obviously had to do a lot of software archaeology, and you were talking about figuring out dependencies and things that hadn't been documented. But I imagine a lot of the code was also not documented, like how does module A work with module B, or that sort of thing. So what did you learn from that project of just how to understand and writing documentation for a software system that doesn't have full documentation? Because I assume you couldn't just build new software without having documentation for the old software. And I also assume that you didn't have much documentation to start. So how did you approach that problem, and what did you learn from it? What can you share with us?
I have learned so much, so much. I primarily containerize your code so that it's easy to ship, so that other developers can use it. In doing so, it will force you to audit all of the dependencies in your project, which will save you so much time in the future. Another thing I learned was that not to use a programming language that you're not sure if it's well established, if it'll catch on. For example, the Super Mongo code, I mean, that is a dead programming language from the 90s, and there is only one manual on that language. There's very little information on the internet, so that was very challenging. And ask as many questions as you can if the senior developer that was working on that previously is still around, which is what I did. I literally made like a Q&A section in the documentation of questions I would ask him and his responses via email in terms of, why do you use least squares fit or these algorithms to process the data in this way? Why are all these assumptions being made? It really sheds a lot of light in that respect. I also learned that there was a Python package that is no longer used. There's like one download of it on SourceForge left, and that's it. And it was the precursor to NumPy, and I was able to find that one download it, and I found a test for one function. There was one function that I wasn't sure what it was doing. Essentially, I think it was processing the data in some way, assuming that the computer was being processed was big endian instead of little endian. For context, most modern machines are little endian, but this was something that was just, it was like, what is going on here? It was not intuitive at all. I found a test in there that they had written to test that function, and that was the only documentation I could find of what exactly that function was doing, because it was not clear to me, even by looking at the source code. I could go on and on about this for hours, but that is the gist of it. Also, don't use a lot of shorthand when you're naming variables and make assumptions about the knowledge that the folks have that are working on the code base. Don't for example, call something like 2FA and then assume that they're going to know what that means, because there were a lot of variables that were named using astronomy conventions and common astronomy concepts that I wasn't familiar with that made it very challenging.
That could be really easy to misinterpret as something else as well. Multiple places that I've been at in the past few years have had a Dropbox. Not associated with the company Dropbox, but every young person that got hired assumed that it was something in Dropbox, and everybody else knew it was something that was used as a common term for many years where to put things. And because of that, there was so massive amounts of confusion. The past 2 or 3 places I've worked have had that. So naming things something very common and not giving someone a guide to what it is can definitely lead to confusion a decade or two later when you don't realize that that is something else now.
Yeah, I just want
Oh
to
yeah.
mention, though, a lot of early languages like Fortran had a limit on the size of variable names.
Oh no,
That's
that's fair
true.
for efficiency's sake. I understand that, but readability in a
Yes.
compiled language, et cetera, et cetera.
Yeah,
That is
readability is
true.
good, but some of these old languages were restricted, and especially in variable names. Especially
Yes,
Fortran.
and something else
Remember
I
early,
learned was, I'm sorry, it was that if especially with Python packages, there are a lot of Python packages that have become deprecated. Um, if you're trying to figure out, okay, is this a dependency, an external dependency, or internal dependency? Because there were a lot of scripts that folks wrote where they're essentially reinventing the wheel, and it was an internal dependency that they wrote, and it might be called the same thing as a real Python package that's used in the rest of the world. So that gets confusing very fast. Sorry. Go ahead.
I was just remembering that back in 1983 when I first started using Unix, the file names were limited to 14 characters, and it was like I think it was like a year or two later that Berkeley came out with the Berkeley fast file system where they could be an arbitrary length.
So this is a newbie question that I deal with often, as in I'm the newbie and I get the question often. And so you've got a piece of software out there that is running, let's say, based on Python or something like that, and Python updates. I work in an environment where I have to update. I am required to update. It is a STIG thing. It's required. So I'm constantly updating things on the back end, be it Linux packages or let's say Python packages for your environment. And give me, I guess, what your experience, I guess, would be. Do you guys test a lot before you throw into prod, and what does that testing look like? My problem is I'm not allowed to test a lot of things because the second it's in a test environment, it's considered production and yada yada. But what is your experience as a software developer when you're building that kind of ecosystem like?
I will say I'm familiar with STIGs. I used to work for the Navy, and it was painful. And STIGs, I had nightmares about STIGs. I'm not even kidding. But other than that, I'm sorry, what was the question again?
More or less this. How do you deal with a constantly updating back-end set of packages when you've got software that depends on them, especially if you're containerizing? Do you just have a test environment that you just run automated unit tests on? Because I'm not a software developer. I don't quite know how people do it. And I work in environments where the software developers have never done it before because it's part of an older ecosystem.
So I would say if you're making the changes yourself, as you're writing the code, it's very important to write unit tests to ensure that you're testing everything as you're adding it. It will save you so much time down the line if you do that. Essentially, for example, when I was converting Mark IV data, which is a custom data format that the astronomers use that literally nobody else uses in the world, to JSON, I literally wrote a test to run this function to convert it to JSON, and then compare the JSON output with an example I had. So it was like a test of this is exactly what the data should look like. So to compare the output JSON file with the example JSON file I had, to compare the two and to return if there was a difference. So basically do a diff between the two. Other than that, I also learned I learned how to use diff. I never knew that you had diff from the command line. I'd always used vim diff before, but that was very helpful. In terms of updating, the dependencies, you can very easily get yourself into dependency hell where you've updated one Python package and it's not working because another Python package depends on that one and they're incompatible now.
Yeah, that chain.
Yeah. If I would say if you can avoid updating them, which it sounds like you can't in that kind of environment, if you can avoid updating them, the best thing you can do is, for example, with Nix, you can pin the specific version of Nix packages of that version that you want, so that you can change the other ones, and that one will never change. And I guess at least if you did it that way, you could test it. So if you can pin all the other versions of all the other packages and then update the one package, the new version, you would know everything else is the same. This is exactly what's changed, and you would know that that's the problem. So maybe
Just
that's how you could do that.
so like isolating
And
the change so that if something does go wrong in your test, you know the source of that problem.
exactly,
Okay, that makes
exactly,
sense.
exactly. And the old-fashioned way of doing things is you always have, you have your developer machine, you have a test server, and then you have production. If you're using containerization in that way, you don't need to maintain all of those types of machines, depending on what you're doing. Granted, we're not working on applications that are being used in a large scale, like Twitter, by hundreds of thousands of users concurrently. But at least that's been my experience. Did that answer your question?
Yeah, no, cool, thanks. I just wanted to get some ideas, and that was helpful.
I think we got some questions in the chat, but I haven't looked at the chat. Let's see. Chuba is asking, what methods do you employ to avoid moving data between servers and process data in a more distributed manner? Do you use anything like MapReduce? I'm not familiar with MapReduce. However, we had a lot of network shared drives where we would store the data, and all the different nodes on the supercomputer cluster and other servers had access to those network drives. That is how we were able to avoid copying data back and forth. In terms of editing the data live as it's coming into the correlator, I can't speak to that effect because I did not work on that side of the equation, but hopefully that answered your question. All right, do we have any other questions?
I think that was a very interesting presentation. One of the
Thank
better
you.
ones we've had, in my opinion.
Actually, here's a question. How did you get to be where you are doing what you're doing? What is your background, if you don't mind?
So my background is in computer science. I am a software engineer, and the way I got to be where I am is they put out a job posting for a software engineer, which I thought was very strange because I thought, okay, it's an observatory. But I later discovered that observatories and a lot of research labs are actually software shops. So all of these scientists, everything they do, they need custom software being made to process the data in the way that they do. And we don't have a lot of off-the-shelf solutions to do this kind of research and work that they're doing. I believe in part of the reason they hired me is because I previously worked for the Navy. So we work in conjunction with Lincoln Labs. There is a there is a classified area. There are folks there with security clearances, and I'm already familiar with that environment. So that is probably part of why.
Very cool. Sorry, current Lincoln Labs employee, former Chandra employee. So I get where you're coming from. Space Ops has a lot of software that people just steal from each other and modify for their project, but there's no commercial origin for a lot of it. That's really cool. That's a good background to have, and it's great that you found a home that allows you to use that background.
All right. Well, do we have any other questions? Oh yeah, Haystack does have open houses about once a year. I think they do them typically during the summer where the public is invited in and you are given demonstrations about the type of work that is done. So that is something that if you're interested in, it's free. It's available to the public. You just have to sign up in advance. I can get a link to the Haystack website.
Hey, Violet, here again, a question you don't necessarily need to know the answer to. Do you know what kind of file formats, if you're sharing data with like Chilean telescopes, is this some sort of a standard open source file format? And for that matter, do you have some sort of high speed connection to Chile that you can aggregate these images together?
Yes, we do have a high-speed, or some form of a high-speed connection there. I don't know the exact specs. And no, we do not have some standard open source format, unfortunately. And open source, I say this in air quotes. Most of the software that we use is made open source to the public, but they don't do a great job about publishing the specs on these data formats so that it's easily accessible to the public. So technically they're open source, but I don't know how to explain it. It wouldn't be very understandable to most people if they don't have a scientific background, if they were to look through this code.
Yeah, these must be just massive data sets.
Oh, yes, petabytes and petabytes of data, even just for one experiment. So that's, one session where they might have 10 telescopes around the world observing the same body in space, which could be like Sagittarius A star, which is the black hole at the center of the Milky Way galaxy. That's our galaxy. And they'll be observing it for 72 hours. And that is one experiment, and that is petabytes of data.
I was in a talk recently where somebody was talking and they did the math on transporting that kind of amounts of data from one place to another, and the math and the cost and everything made it cheaper and faster to load the hard drives onto an airplane. And I don't mean a direct flight. I mean just like to ship the data, physically ship the data, and then correlate it at the at the site. I believe Event Horizon has done that before, where they've had the hard drives literally had to be shipped, not transmitted over wire, not because of security, but because that was the best way to get that much data.
Sometimes sneaker networks.
Never underestimate the bandwidth of a station wagon loaded with hard drives. The latency, however, is a problem.
Yep, there you go.
Yeah, most of our data is literally shipped back and forth around the world, such that we have actually custom hard drives that are designed to be more hardy, and we have quite a few that are helium cooled, which I'm sure nobody's ever heard of before, but that's the kind of requirement specs they need to have to withstand some of the environments that they are in. For example, the ALMA Observatory, which is in Chile, is very high elevation. I don't remember off the top of my head the exact numbers, but it's very high elevation. So the helium cooling helps with that. Also, we have another observatory that's on the South Pole. So all kinds of crazy environments that this hardware is exposed to. Some of our data is sent over the wire, so to speak, and there are issues all the time with that. The data is stalled, and we need to restart the transfers. Some of the data was not received. Some of it was received in the wrong order. And with physical media, we have the same issues too. Sometimes we get hard drives, and they look like somebody put them through a blender, and it's just it's a lot.
Yeah, the key thing about ALMA and the other observatories there in the Chilean high desert is it's above the moisture, so that the sky is transparent in other frequencies. Going back to the false coloring of images, if we gave you infrared photographs that were in the infrared, in their natural color, you couldn't see them.
Exactly.
Same for ultraviolet. So, and don't get me started about gamma rays
and X-rays. Fair.
Yeah, I think we'd moved out of the building that we shared with your old X-ray telescope before you joined them.
Were you over in Draper at the time, or? Yep.
Yeah.
Okay.
It was our VP of IT that your VP of infrastructure consulted with. How do I get reliable, high-speed, yada 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 installed in this tenancy? And our VP IT gave him such a good briefing on how to deal with the landlords and the contractors that he arranged for somebody to give a bunch of us a tour, and it was lovely.
Yeah, it was great until Draper kicked us out a few years ago. That was a fun way to learn how to build a whole new operations control center up in Burlington.
Yeah.
Oh gosh.
Hopefully somebody saved the notes from when they built that one.
Yeah, I would like to think so.
Oh, something else I forgot to mention is that the Haystack Observatory was featured in a movie about aliens. So that's just a fun bit of trivia. I am completely...
Recording is on.
And if it isn't as big as Arecibo was, it's not going to have enough gain to get them to hear you. And it's rather dubious that Arecibo's transmitted message, which wasn't properly coordinated ahead of time, possibly taking advice from Grace Hopper. An interesting piece of Haystack's pre-Haystack history that ties in with that X-ray telescope facility as well. the MIT Geodetic Observatory was founded in the Middlesex Fells in Malden, Medford, Stoneham area, because the the bedrock erupts ferociously there. So good foundation with a nice horizon. And they collaborated with Harvard Smithsonian back when you could like do observation from outer Harvard Square, because geodesy and astronomy have to bootstrap each other. And so they ran a telegraph line between the two observatories, so that Harvard Smithsonian could tell MIT geodesy when it was local noon here.
Yeah, Jerry, how long was the recording out?
Interesting.
I never noticed when it dropped out, but I just noticed that you started up again.
Yeah, my Jitsi dropped off completely, and I had to restart Jitsi, and I started the recording. But I got most everything.
You and
Yeah,
me
it sounds like
both.
you got all of the talk, which was good.
Yeah, I definitely got all of the talk. I find that these recordings do that. That's why we stopped doing the live stream, because it would stop in the middle of the stream and then I couldn't get it restarted, which is the reason I went to the recording rather than the live stream.
So it looks like we have a question in the chat from Chuba. Sorry if I missed you saying this earlier, but what programming languages do you find yourself working on more frequently when you're not working on Fortran and SuperMongo? I would say Python, definitely the most. Scientists seem to love Python. They love Conda, the Conda version of Python specifically. And other than that, C and C++. And I do everything I can to sneak in other languages in there when I feel that they are appropriate, like Nix, to containerize environments. I even have a Haskell code. I have a Haskell tiny program to convert time into a decimal format. So for one of the projects that I worked on.
So here's one that I think we should ask every single person that comes to this. When you're using Linux, because some people are, Mac OS or Windows, whatever, what is your daily driver OS when you're using Linux? Both home and mostly work, if you use Linux primarily at work, but also at home.
So at work, primarily I use Ubuntu 20.04. There is a hodgepodge of OSs that other folks use. The Linux users are very fractured at work, but Ubuntu was the one that most people could agree on, so that's why I used it at work in order to have some commonality there. It helped with collaboration. But at home, I daily drive NixOS. I love NixOS. I could give a talk on that, but you already have a talk on that. So that is my favorite Linux operating system. I would say my second favorite, which is what I have on my Steam Deck, is Arch with the AUR enabled, which unfortunately you can't do on the Steam Deck because they have futzed around in there with the OS. But I love NixOS. It is very customizable, and it is actually, if I were to start my own company and create test and production environments, I would definitely use NixOS because so remember how I mentioned I'm able to create declarative containerized environments with Nix? With NixOS, you can do that for the whole operating system. So that's how I would spin up new servers if it were up to me.
So throw the config in Git and just pull it down from there and every time you can just create your new server based on that. I'm sure there's a billion ways to do that. And I do remember the NixOS talk because it was live at MIT when there were live in-person things, which means it's about a half a decade old. It might be time for a new one.
Oh, you
No,
had one a couple
we
months
have
ago.
one that recently was Ben Callis gave
Oh, and I totally missed it. So
two talks,
ignore me.
both
Sorry.
were in January. The one was on, they were both on Nix, but one was on NixOS and the other was on the distro. And again, Ben is coming back to us in August.
Cool. Sorry, missed it.
All right. Do we have any other questions? All right. So I guess I would like to close off with like I said, federal funding has been cut for a lot for the sciences, especially at MIT. It is MIT's in the middle of several layoffs, it would seem, which have included me. So if you want me to work at your company or know somebody who does, I'm available. So
Yeah, for the sort of projects I used to do, the skills you've developed would be useful, but I'm mostly retired. But the sorts of things that Brendan's talking about in the financial world, where they're having to convert old platform, old COBOL or whatever, because they had the same flavor of the month programming languages in finance also. Those testing skills and conversion and moving the data between the old system and the test system and the new system, those skills would be directly applicable to corporate finance system legacy remediation projects.
thank you. That's helpful to know.
At Fidelity, we delivered several. The average project this size is canceled projects successfully, partially by having weaponized senior vice presidents who could kick a contractor hard where it hurt, and partly by having rigorous testing processes such as you were describing.
It also goes without
you.
saying that I'm sure you've already looked at the lab, but I'm sure they have positions from time to time that fit exactly what you're looking for.
Oh, at Lincoln Lab?
Yeah, I mean, they've got so many positions all the time, but I don't know. I'm in the IT space, not in the development space, software space, but they do have stuff. I don't know if you've looked there, but since Millstone is right next door to you and the lab is down the street, by 20 miles, you might want to consider looking if you're looking.
And one step beyond Lincoln Labs, the MITRE Corporation is a quasi non-governmental spin-off from the Air Force Base that does a variety of work, and they're probably having layoffs too. But
MITRE was originally part of the lab, and
yes, I know the whole history.
MIT rejected engineers or MIT rejected employees was the original
MIT Radar,
misnomer.
and it does not stand for MIT Radar Engineering. Because that would be a trademark problem with MIT's lawyers, because this was trying to be even more arm's length than either Draper or Lincoln Labs was.
Yeah.
Because the Air Force, but yeah, so when I was at MITRE more decades ago than I want to admit, one of my office mates had a 00 badge number because she was at Lincoln the day people were called to the auditorium and told on the way out they were going to get MITRE Corporation badges. Congratulations. And then
That's fascinating.
Then she took 20 years off to raise a family, and asked if she could come back to work, and they said yes. And so she had a classic 00 starts with a 3 badge number from the original Lincoln Lab conversions, without being a cigar chomping electrical engineer.
That is very cool.
And she was just neat people. We had a fun little computer security group back when computer security was still fun.
I'm surprised they would have allowed her to come back and remembered her after 20 years. That's amazing.
These places have a long institutional memory.
Yes. I mean, and it was, and they were actively trying to get a little more diversity around the place, even though Reagan was president, because it was Massachusetts. And so a late middle age, almost grandmother, ticked a couple of boxes. But she was good. She was neat people, and what was great to have on the project. But yeah, there's a long corporate memory there, because their job is to remember why the military built this way 20 years ago, now that we want to upgrade it or replace it. Lincoln Labs comes up with the new ideas, and MITRE has to help the Air Force or whatever other branch of government manage the acquisition contract, coordinate with the testing validation contractors to keep an eye on them. It's sometimes not the sexiest work, but sometimes there's some prototype programming or fun work that isn't just beating the contractors, but sometimes beating the contractors is very satisfying, because catch a mistake when it's cheap to fix the mistake saves the taxpayer money.